Hi, I'm Rujin Song, a postdoc working with Professor Mike Scarpella at the University of Utah. I will talk about oxygen annealing-induced changes in defects within 010 beta-gallium oxide epitaxial films measured using photoluminescence. The identification and manipulation of defects in gallium oxide are important. Thermal annealing on the oxidizing atmosphere is found to increase the resistivity of gallium oxide. The relation between resistivity and the oxygen partial pressure applies in single crystal growth and C-film deposition. Also, the post-annealing. For many decades, the reduction in electron density upon oxygen annealing is attributed to a reduction in oxygen vacancy, which was assumed to be a shallow dollar without direct evidence. However, density functional theory calculations, which in recent years have significantly increased the accuracy of calculations of defect charge transition levels, indicate that oxygen vacancy is a deep dollar. Thus, oxygen vacancy should not be the primary defect responsible for the resistivity increase. Note that the silicon and the hydrogen impurity are the leading candidates for background n-type conductivity. Although direct evidence, experimental evidence of changes in defect concentration is sparse, electron paramagnetic resonance spectrum show that oxygen annealing induced the RR1 center, which is assigned to the double negative charge states of gallium vacancy or its relaxed configuration. Positron ionization spectroscopy demonstrates that oxygen vacancy concentration is increased on the oxygen annealing. Despite this basic insight, distinguishing main defect accounting for resistivity increases and fully investigating the formation, diffusion, and the complexing mechanism involved remain to be completed. Photoluminescence spectroscopy is widely used to characterize defects. Three-band PL are observed for a majority of beta-gallium oxide samples upon above band gap excitation, namely the UV, blue, and green. Recent computations have shown that many different point defects and complexes offer internal transitions which should fall into the observed green and blue bandwidths and be vibrologically broadened. This may ultimately prevent the unambiguous attribution of any of these peaks to one particular defect or complex. Besides, both wide and sharp red luminescence features are observed in some gallium oxide crystals. In this work, we use photoluminescence spectroscopy from MOVPE growing homoepitaxial 010 gallium oxide film subjected to oxygen annealing. Annealing was conducted in 180 N in a quartz tube furnace to control any sample-to-sample variation. The same sample was measured in PL, then annealed, and the increased temperature, and the next increased temperature. The Hall effects are used to characterize the carrier density of the as a growing film and film after annealing at 1100 degrees C. Photoluminescence are performed using both 214 and 266 excitations, which provide depth selectivity. As the annealing temperature increases, the total PL yield decreases continuously, which we take as an indication of increasing the non-radiative process. Also, the UV intensity changes in nearly the same way as the total PL yield, indicating the dominant process to form self-trap holes. By normalizing the emission bands to UV emission, we should remove the influence of non-radiative channels on excess carrier population, and thus we can consider each radiative channel. According to the phenomenological rate equation of holes after photoexcitation, holes were captured by oxygen site, acceptor 1, acceptor 2, and non-radiative centers by ignoring the hopping of the bonded holes among them due to the lower concentration. According to the de-trapping energy of electron and holes for blue emission, we propose that blue emission is related to transitions between shallow donor and deep acceptors. So does the green emission. Due to the constant concentration of oxygen sites, we could normalize other emissions to oxygen to UV emission. Thus, the relative emission intensity is proportional to the relative defect density responsible for it, since the capture rate coefficient of defect should allow change. The decrease of carrier density upon oxygen annealing suggests a decrease of shallow donor or increase of acceptor. We have established that through Hall, CV, and Sims that silicon is a dominant donor in our field. Silicon dopants will only diffuse instead of be deactivated upon oxygen annealing. Thus, the compensating acceptor are more likely to increase with the annealing temperature. The dependence of electron density on oxygen annealing arises from acceptor density, and its related PL intensity should go up with higher acceptor concentrations. In fact, the relative intensities of blue and green emissions do change as a function of annealing temperature. In the computation of defect formation in the bulk, gallium vacancy exhibits the lowest formation energy among the native acceptors under oxygen-rich condition, especially for the N-type doped films where the Fermi level approaches the conduction band, combined with the fact that the reported positron ionization results, the indicated intrinsic nature after neutron irradiation, and we ascribe the increase of blue emission to the increase of oxygen gallium vacancy concentration is consistent with the mentioned finding. Also, the increased blue emission might also come from intrinsic defect. We have other evidence that supporting the gallium vacancy forms and compensates donors. We know in the absence of the mass transport to or from surface, smoothing to reduce the surface area rather than increasing it would be expected. The changes in the morphology from linear feature to the hair local feature after annealing and 1100 C do hint a significant mass transport process involves the surface. No etching or decomposition and the desorption of carbon dioxide is expected, and this temperature, pressure, and oxygen partial pressure according to the thermodynamic. The 1 atm of pure oxygen over pressure implies sufficient oxygen atom to grow a similar number of molar layer of gallium oxide per second with sufficient gallium is supplied. Given this consideration, we propose that this change in morphology results from gallium atom diffused to the surface and react with the oxygen from the air to form a new unitary cell of gallium oxide, which in hair-lock morphology. If the auto-diffusion mechanism of ganglion for ganglion is Y substitution ganglion complex or 2 ganglion vacancy plus 1 ganglion interstitium, it could be equivalently be viewed as a formation of ganglion vacancy and or complex and surface have one activation energy and followed by its indiffusion under a larger activation energy. Interestingly, we found that the red luminescence originating from chromium is observed near the surface after a linear at a high at 1015 and 1100 degrees C, but not observed at a low temperature. This correlates with the diffusion of chromium from the substrate into the field. This process is consistent with the formation of ganglion vacancy and the diffusion through ganglion vacancy, since chromium is expected to substitutionally sit on ganglion sites. The ion implanted silicon, tin, and germanium, which also diffuse at a similar temperature, are concentrated near the surface upon oxygen annealing, indicating that the formation energy of ganglion vacancy at the surface is smaller than that of bulk. The situation could be that the ganglion vacancy forms near the surface and diffuse into the bulk, while the chromium impurity diffuse into the film by exchange position with the ganglion vacancy, thus move toward the surface and be detected by PL. The activation energy of the UV absolute intensity in Leo surface is 2.53 and 1.34 eV in deeper field, which represents the quenching of UV peak by increasing the non-radiative recombination, accompanying higher temperature annealing. The EA extracted from the green emission is higher than that of blue emission, suggesting different defects or mechanism between them. Considering the as mentioned experimental phenomena, we try to find the evidence that the surface formation energy is relatively small and the bulk diffusion process followed a higher barrier value in the depth direction. The blue peak seems to exhibit only a slight change of EA, while the green have a stronger surface versus bulk contrast. Further work will be necessary to determine more accurate activation energy for the formation, reaction, and transport and the surface and within the bulk. To summarize it, the overall PL yield and the PL yield decreases in the same way upon annealing. The blue and the green to UV intensity ratios exponentially increase with annealing temperature. We extract an activation energy of 0.7 eV for blue emission for all depths in the field, suggesting a bulk process, while the green emission data hints a differentiation between surface and bulk. The chromium impurity are observed to diffuse into the epitaxial field at high temperature, possibly by substitutional diffusion mediated by ganglion vacancy, including the morphology changes of the surface. Our findings are consistent with the formation of ganglion vacancy and its complex as a major defect process during oxygen annealing. Thank you. That's all.